Alright guys, let's pick up from where we stopped. Paper 4 of October-November 2023, variance 4.2. Okay, in our last session we looked at question 1. Now we need to look at question 2. Okay, so question 2, we have cobalt and copper are transition elements. Copper has two naturally occurring isotopes, copper 63 and copper 65. Cobalt has only one naturally occurring isotope, and that is cobalt 59. Okay, question A1. Complete table 2.1 to show the number of protons, neutrons, and electrons in the cobalt 59 atom and the copper 55 plus 2 ions. Okay, so number of proton, I think it would be better for us to get the number of proton from the periodic table, although you should know that cobalt is element 27 and copper is 29. So let's quickly look at the periodic table to get that, to confirm that 27 for cobalt. So yeah, 27 is the number of proton for cobalt, 29 is the number of proton for copper. Okay, so we've gotten that. So you always use your periodic table if you are in that. Periodic table is part of the part of your exam. Okay, so we rotate back and let's see how we can start answering our question. Okay, so we are moving to question 2. So question 2, here we are. Okay, so we are looking at question 2. Number of proton 27 for cobalt and 29 for copper. Okay, number of neutrons for cobalt, you are going to do 59 minus 27. 59 minus 27, I'm getting 32. 32 it is. 59 minus 27, you do the same for this, you do 65 minus 29, 65 minus 29, and you have 36, that is 36. Okay, you know, for every atom, that's cobalt atom, for every atom, number of protons must always be equal to number of electrons. Okay, so it's easy. Number of electron 27. However, this is a plus 2 ion for copper. Plus 2 ion means that it has lost 2 electrons, such that it has 2 more protons than the electron. So you could take away 2 from the number of electrons and you get your answer. So taking 2 away from the number of electrons, number of proton here, take away 2 from it, you get number of electron. That makes it an ion. So 27 it is. 27 it is. Number of electron 27. Please note that for every positive ion, number of proton are usually more than number of electron. For every positive ions are usually referred to as cation. Okay, so we call them cation. So a cation is an ion that has more proton than electron. All right, so 3 marks. Every correct row, row 1, row for protons 1 mark, row for neutrons 1 mark, row for electrons 1 mark. Correct. Okay, so we make progress to table 2.2. Roman figure 2, and the question table 2.2 shows the relative abundance of the two naturally occurring isotopes of copper. So we have copper 63 to be 70%, copper 65 to be 30%. What this simply means is that anytime you have, it is possible for you to have copper atoms in your hand. Have copper atoms handy. Count the number of copper atom. I'm saying it is possible for you to count the number of copper atoms in your hand. Let's say there are 100 copper atoms in your hand. Naturally, you are going to have 70 of them to be copper 63, and you're going to have 30 of them to be copper 65. That's what the idea of relative isotopic abundance is about. Now we are to calculate the relative atomic mass of copper to 1 decimal place. Okay, so let's remind you the formula. How do you calculate? So you just look at the percentages and you take average. So you are doing 70% times 63. 70% times 63. You add that value to the 30% times the relative atomic mass of that copper, and that is 65. Okay, we do this and everything, we add them up over 100, and that gives us what we refer to as AR, relative atomic mass. Okay, so that will be the relative atomic mass. So you could easily solve this out. 70 times 65. If you punch your calculator, you're going to have 4410. 4410. You add that figure, punch your calculator again, and get 65 times 30. You have 1950. 1950. Okay, so everything again over 100, then you sum it up. When you add 4410 to 1950, you are going to have 6360. Divide by 100. This is easy. These two zeros strike out, you push this, you push this. Okay, so you have 63.6. That is to 1 decimal place. The instruction says to 1 decimal place. Okay, so if you are to round to the nearest whole number, it's going to be 64, but that's the way the instruction says to 1 decimal place. So you leave your answer at 63.6. Okay, so great job. Now we make progress. One physical property of transition elements such as copper and cobalt is that they are hard. Other metals such as lithium are softer. Okay, so those are physical properties that are different. Physical properties of group 1 metals that are different from regular metals. Now state 2 other physical properties of copper and cobalt which are significantly different from. Okay, so you see, if you put lithium in water, it's going to float, but you can't try that with the same amount of copper, or the same amount, or the same mass of cobalt. Get the same mass of lithium the same mass of copper, put it in water, lithium is going to float, the copper is going to sink. Okay, so that's about density. Okay, so you say state two other physical properties of copper. So you say you have higher density, so you want to learn to use comparative adjective, higher density. Don't tell us it has high density. You know you are comparing two things, so you say it has higher density. Okay, perhaps we could make it better. Copper has higher density. Okay, just telling us that the high density, it does not make sense. You are comparing two things, you want to show the comparison. Copper has higher density. Okay, has higher density. You could include higher density than lithium. Okay, higher density than lithium. Okay, so that's density. Then we can also think in terms of melting point, boiling point. Okay, that melting or boiling point, obviously copper has higher melting point than lithium. Okay, we could use boiling points, melting points. So copper has higher melting points, copper has higher boiling points than lithium. Okay, higher melting point, higher boiling point than lithium. All right, that's a great job we have done. We will make progress now with the next question. Both copper and cobalt can form colored compounds. Yeah, that's a property of transition metals. Now some of these compounds contain water of crystallization, and that's why they are crystals. Okay, they form water. When they contain water of crystallization, they become hydrated. Now define the term water of crystallization. Okay, so water of crystallization is the water present, a simple water present in a hydrated crystal. Okay, water of crystallization, the water present in a hydrated crystal is what we refer to as water of crystallization. Water of crystallization is the water present in a hydrated crystals. Okay, water present in hydrated crystals, they are usually chemically combined with the regular salts to form the crystals. So water of crystallization is the water present in hydrated crystals. Okay, is the water molecule, let's add that, is the water molecules. You know, water is a molecule, covalent compound. Water molecules present in a hydrated crystals. So your ability to identify that water molecules present in hydrated crystal, your ability to mention water molecules or water gives you 1 mark. Hydrated crystals, 1 mark. Alright, we are making progress now. Now state the color and formula of hydrated cobalt 2 chloride crystals. Okay, so cobalt 2 chloride, hydrated cobalt 2 chloride is pink. Okay, pink it is pink, while the anhydrous is blue. Okay, so the anhydrous of hydrated copper 2 chloride is blue, but the hydrated is pink. So generally, if you want to use it to test for water, the anhydrous, we usually use the anhydrous. In other words, anhydrous simply means that it's without water. Anhydrous. Okay, this is what we mean. Anhydrous. Okay, so the anhydrous means is without water. So anhydrous cobalt 2 chloride is blue. Okay, the moment you add water into it, it changes from blue to pink. So that's the test for water. We either use anhydrous cobalt 2 chloride or anhydrous copper 2 chloride. Okay, so what's our formula? Cobalt, capital C, small letter O for cobalt 2 chloride. You put that and you put a dot, okay, to show the hydrated. Now the moles of the water molecule, or the number of water molecules, is 6. So you have 6 molecules of water. 6 molecules of water, and that becomes the formula. That becomes the formula for the hydrated cobalt 2 chloride. Okay, so that's done. So we make progress now. State the color change seen when a few drops of water are added to anhydrous. Oh, I didn't get to. Okay, I didn't even know that it was mentioned here. I would have just signified the spelling of what I was referring to. Okay, so we go back to our question. State the color change seen when a few drops of water are added to anhydrous copper 2 sulfate. Okay, so copper 2 sulfate, anhydrous copper 2 sulfate is white. The color is different from cobalt. So anhydrous copper 2 sulfate is white. At the moment you add water into it, it changes to blue. So from white to blue it is. Okay, from white to blue it is. Alright, please, you should be careful with the color. If it's cobalt 2, it changes from anhydrous cobalt 2 is blue, it changes from blue to pink when you add water. And for copper 2, changes from anhydrous copper 2 sulfate is white, changes from white to blue. Now state how these color change can be reversed. Okay, so this is actually a reversible process. Whereby you can this particular guy now, you can heat it up. When you heat it up, all this water will go away as steam. Okay, you heat it up, all this water will go, the 6 molecules of water will go away as steam, and when they go away as steam, then as at that time we refer to it as anhydrous. Okay, so for it to come back, just add water, you see it's spitting, especially when it is that time that you just stop heating. Add water, you see it's spitting because the process then will be exothermic. Alright, what we are saying here is by heating to reverse the process. State how this color change can be reversed. In other words, we have taken it to blue. How can we take it back to water? By heating. As the time it has turned to blue, it's no longer anhydrous but hydrated. Okay, so changing hydrated back to anhydrous will mean that we heat. Okay, so by heating the hydrated crystals, by heating the hydrated crystals, by heating the hydrated crystals. So this is good job, well done guys. I'll see you in our next session where we'll be answering question 3.